So we're going to be talking about how to remotely exploit iOS and Android devices via a bug that we have named Broadpwn. There's been quite a lot of buzz about Broadpwn recently, so we want to tell you why we think it's a very special, interesting and powerful bug, and also tell you a bit about the process that led us to this bug. But first of all, let me just introduce myself. My name is Nitai Artenstein. I've been doing reverse engineering and vulnerability research for about as long as I remember. I'm mostly interested in Android and some low-level systems such as basebands, Wi-Fi chips, bootloaders, and I've been doing that for approximately the last 5 years. So we are going to be talking about Broadpwn as a remote exploit, the first remote exploit in quite some time to be public. And first of all, we're going to be defining what a remote exploit actually is. So in our opinion, a remote exploit is not a browser exploit, and we're going to be explaining exactly why. And we're going to be discussing how we found this particular exploit in a specific and interesting attack surface that was almost unexplored until now. And we'll be concluding with how we leverage this bug that we found into the first fully functional remote exploit to be public and in recent years. So first of all, what a remote exploit isn't. We've all been hearing the news about various government agencies in some countries attacking dissidents and other people with browser bugs, sending them SMSs with malicious links. Now, we believe that if you need the victim to click a link and to actually interact with any particular link or whatever you're sending him, then that's not a remote. A remote is something totally different. It does not require social engineering. So let's define what a remote actually is. So these are the three laws of remote exploits. I suggest you take a picture because there's going to be a quiz later on. Sorry. Yeah. So memorize these three laws. First of all, a remote may not require any human interaction to trigger. That means you can't click on an SMS, a link, you can't open an email. That's not a remote. That's actually, we consider it to be a local exploit. Then, a remote may not make assumptions about the system that it's attacking. And there's a very simple reason for that. When you attack a target remotely, your attack surface is much more limited. You have a much more limited interaction with the target. So supposing you're attacking a kernel or a browser, you normally have some kind of interface to get feedback, to get some kind of data about the state of the system. It helps you with assumptions you need to make about the exploit. You can't make these kinds of assumptions in a remote. And the third important rule is that a remote must leave the system in a stable state. That's because you want to be persistent, you want to keep a stable presence, and you don't want to alert the target that you're attacking. So these class of bugs have been very prominent during the early 2000s. We all remember various worms and malware in Windows. During those years, you really didn't need to do much other than connect to the internet, and your computer was already owned. And you didn't know anything about that happening. And these days are long gone. So why? Well, there's been a lot of mitigations and awareness about remotes. And if we look at the three laws they're difficult to keep up because to find a remotely exploitable bug that doesn't require any interaction from the user is almost impossible because the attack surface is much more limited when you're attacking a target remotely. It's also difficult because you need to make assumptions about the system because you have ASLR. ASLR randomizes the address space, so you never actually know for certain where any addresses are. You need some kind of a leak to know that. And that's a problem because you have a limited interaction with a remote target. And another issue is that you cannot make any mistakes against remote targets because normally, if suppose you're attacking a kernel, if you crash it, there's a panic and you're gone. So you're in a difficult position where you cannot make any assumptions and yet you cannot crash the system. So obviously this is a very difficult goal, and late last year Google Project Zero have announced a special bounty for remote exploits for Android. It was $350,000 if I remember correctly. There was not a single submission. So apparently either this is too low for that kind of exploit, or it really is as hard as we think. So in attempting to resolve this problem about how can we get a remote exploit against fully hardened mobile phones such as Android and iOS, we started looking at the system from a higher level. So we have the main application processor both in Android and iOS, and there's a lot of mitigations going on there, a lot of hardening. First we have DEP and ASLR, which both prevent code running from arbitrary places in memory and prevent us from making assumptions about the memory space. And there's various new mitigations such as PAN and PXN, which prevent us from jumping to userland from the kernel or accessing data that we're not supposed to from userland or from the kernel. So that's really hard work for us to develop an exploit in such conditions, especially a remote one. So we've started looking around the neighborhood, looking at a mobile phone but not at the main application processor. And we've come up with kind of two alternatives, two other chips that exist both on iOS and Android that have a very extensive interaction with the application processor. So one of them is the baseband, which handles 3G and 4G communication along with many other tasks. And another is the Wi-Fi chip. Both of them have a connection via various interfaces such as PCIe to the application processor. So they're in a much more convenient position to attack the kernel, the main system. So we started having a look at those two subsystems. And first of all, we've considered basebands briefly. Now, basebands are a fascinating attack surface, very interesting, very fruitful ground for bugs. But there's a problem of fragmentation, especially recently. Up until a few years ago, Qualcomm were the market leader. They were dominating this field. But recently, there's been quite a few new competitors grabbing popular devices. iPhone have moved to Intel chips. Samsung have moved to the Shannon basebands. Google Nexus are still with Qualcomm, but other lower-end LG and HTCs have moved to MediaTek. So really, if you develop any sort of exploit or find a bug in a baseband, that would not get you very far in terms of the percentage of devices you would be able to attack. So we've looked at the Wi-Fi chip, and there the picture was very different. Broadcom are a clear market leader. There have been in all the iPhones since the iPhone 5. Almost all Samsung Galaxies and Notes, all of them that we've checked. That's the S3 all the way through S8 and all the Notes. Most Google Nexuses since Google Nexus 5. And there's been some various LGs and HTCs that use them, although not universally. So obviously this is a much more interesting attack surface, because you don't have to repeat your work. If you find one bug, you can use it in plenty of places. So, and there's a bonus here. We've discussed how ASLR makes remote exploits almost impossible without some kind of an info leak or an ability to brute force the address space to find addresses. And in this case, that's not a problem, because on the Wi-Fi chip, all memory is read, write, execute. There's no DEP and no ASLR. It's basically a 90s party. So let's start diving into the Wi-Fi system on chip and see what makes it interesting. So first of all, there's been a lot of work about this particular system in the past, and we've learned a lot from what other security researchers have done. So the most recent work is Gal Binyamini of Project Zero, who has done some amazing research about this particular Broadcom chipset. He's also found some few very nice bugs. Then there was the Nextmont project by the CMO group, if I'm pronouncing it correctly. And they've developed a very nice tool set for hooking and debugging Broadcom chipsets. And that's also been extremely helpful for us to debug and to develop the exploit. There was a bunch of Israeli researchers in Recon who were kind of the pioneers in this field. They were, I believe, the first ones, together with Andres Blanco, to actually work on patching the baseband, the Broadcom chipset, and making it do various things that it's not supposed to. So I'd like to say thank you to all these researchers, and this is an example of how we all help each other with the research we do. So another helpful thing about those Broadcom chips is that Broadcom's Wi-Fi division was recently purchased by Cypress, who've open sourced a lot of the specs. This is the diagram for the Broadcom 4354, which powers the iPhone 6. And I've simplified it for you. So a basic architecture of a Broadcom chip is so we have an AXI backplane, which connects the various parts. Then we have the main microcontroller, which is an ARM Cortex-R4. Then we have a D11 PHY chip, which handles RF and actually processing packets from over the air. Then we have PCIe or SDIO, which connect this whole system to the main chip, to the main processor, via PCIe works via DMA. SDIO is our proprietary Broadcom interface, which is, I believe, slowly being phased out. And then we have about 900K of RAM and ROM on Euro chips. RAM actually holds most of the instructions, most of the code. ROM holds most of the code. RAM is mainly for patches, for bug fixes. So basically, every once in a while, there's a jump to a function table, and that's where the function table is in RAM, and that's where the Broadcom people can put any jumps to newer code that they want to patch. So to reverse this firmware was pretty extensive project. It uses a proprietary real-time operating system known as AgenDRTE. It was kind of a pain to reverse it. The code is pretty complicated, and there's a lot of functionality which you need to reverse from scratch. But fortunately, the sources leaked about 5 years ago. And digging through Google with various function names led us to these proprietary Broadcom sources, which were included with a project known as VMG1312. Apparently, the Broadcom drivers were compiled rather than supplied as in binary form. which means that a lot of the source code is available. So this really helped us gain some perspective into the system. So after getting a perspective about the basic functionality of the system and what it does, we wanted to dig in and look at the right attack surface to actually find a place that could give us a remote bug, a remotely exploitable bug, because this was the purpose of the whole project. So now's the time for our first quiz. Who remembers the first law of remotes? You can just shout it out. Yeah, you can't interact with humans. So what we needed in security terms is an exploit, a bug that doesn't require authentication in order to trigger, which means that the user actually doesn't need to actively connect or log into any specific place or connect to an access point. So that's a rather tall order, and let's see how we approached it. So here's some basics about the Wi-Fi association process. Before you actually reach WPA2 and any of these encryption methods which are supposed to protect your traffic, there's a very simple packet exchange between the station, between the client and the access point. And that's the association process. It begins with a probe request on behalf of the station, the client. The client basically is looking for access points to connect to. If an access point is nearby and it's configured to allow anybody to, if it's configured to advertise its presence, then it sends out a probe response. Then there's an exchange of an obsolete set of packets known as auth open sequence, which used to be there to implement WEP, which is now obsolete. And then if the client actually wants to connect to this access point, it issues an association request. Then the access point, if it wants to let the client connect, issues a response, and then they start to exchange data. Now, the authentication process is only inside this last phase, within data. WPA2 is implemented on top of this association process. It's not a part of it, which means that there's no authentication in all of these phases that we've described. Now, I know you're asking a question. There's a catch here, right? Anybody wants to like shout out what's the catch? Because probably somebody must be thinking about it. Sorry? Yeah, okay. One issue here is that you must be thinking the client actually needs to choose to connect to an access point to initiate this process of association. And that's basically true, except for a mechanism built into probe requests in Wi-Fi, which is that a client actually advertises the SSIDs, the access point names that it's looking for. So for instance, if you are Bob and you've connected to an access point called Bob Home, every once in a while you'll send out probe requests, if you're not associated, with this name of that particular access point. So let's see an example from the real world. I was sitting in one of the halls just now with AeroDump to look at unassociated clients looking for their home access points. Let's have a look at what I saw. Yeah. So the hall was actually almost empty, but look at all these names I'm seeing. Look at all these unassociated clients sending out names of SSIDs, of access points that they're looking for. By the way, there's quite a few interesting names here. If you look carefully, you'll see an access point and I think it was just here, a query for an access point called Stuxnet. And every once in a while, it's pretty interesting to just open arrow dump and look at what people around you are looking for. It might tell you a lot more about them than you think. So this thing actually lets you treat the association process as if it doesn't require any interaction. So long as a victim has connected to an access point in the past, and if you stay around them for, let's say, a minute or two, you should be seeing one of these. And the beauty of this thing is that there's no authentication involved in this process. So even if it's a WPA2 or a radius access point with the maximum possible provisions for authentication and security, you still don't reach that phase so long as you find a bug in this particular protocol, because any authentication is done only after this initial exchange of packets. So we've convinced ourselves that this is an interesting attack surface. Sorry. Yeah, so this is an interesting attack surface. And now we'd like to begin to examine how to actually attack it. What do we look for? So basic Wi-Fi 802.11 packet looks like this. It includes basic header. It's pretty small. It only includes addresses and some bits denoting the frame type and other info. There's not much potential for bugs there. But the real info, the real meat carried in the packet, and we're talking about packets for the association process, the real meat comes in a variable length addition to the packet. It's known as an information element. It's appended to the end of the packet, and you can have as many information elements as you want in a packet. That's the way that access points and clients exchange information between them. And the way that they're constructed is it's basically just a simple TLV, 1 byte for type, 1 byte for length, and then a variable length data area. And you can have 5, 10, even more of these IEs in a packet, depending on the capabilities of the access point and the client, what they want to tell each other. So this is an interesting place to look for bugs, because in old and insecure software, it's a known minefield that sometimes programmers don't particularly look at the length fields. They don't remember to check whether the buffers they've allocated are big enough to hold the info that they're copying from the packet. So naturally, that was an interesting place to look for bugs. So we wanted to narrow down our reverse engineering process to those specific places where we think that such bugs could be found, to places that actually handle that parsing of those particular information elements. So that was made easy by the design of the firmware of the code. It's very modular. You can see that it's divided into particular modules which are being loaded or attached when the chip boots up. So that made it very easy to start having a look and pinpoint particular protocols that we're interested in. And we found this function, which helped us a lot. This is a function which it's called the IEM add parse function. And this handles, this basically registers a callback to handle IEs of specific type. And you can see there's a field IEM type, which denotes the IE that the function is supposed to handle, the callback. And then there's the subtype field, which tells you which kind of a packet it is, which means whether it's an association response or request or probe request, which packet is it in the association process. So it was very convenient to narrow down the protocols which we thought would be particularly complicated or difficult to handle correctly. the data being transferred in the packets of the association process. And we've mapped XREFs for particular modules handling protocols, which seemed interesting. Now, this was also a tricky part because, for instance, you can see some references here to CCX, TDLS, which are protocols which are not handled before authentication. So that was not really relevant for us. We were looking for that small specific subset of protocols which are handled during the association process. And that's how we reached our bug eventually. So there's a protocol in Wi-Fi known as the wireless media extensions. We don't need to really go into too much depth about what this protocol does. It's designed to let the access point know about quality of service requirements. For instance, if the client is handling video or voice over IP, then the access point can give priority to the packets which handle traffic which requires good performance. So there's a field in which the client specifies what are its requirements, whether it supports WME or not, and this is being parsed as part of the association process. And we've come across this function. If you look at it for a second, it basically shouts out bug. And again, this happens a lot when you deal with embedded systems. You find bugs just like they used to look in the good old days. So when I was starting out, you basically just had to grep for memcopy in a source code, and that's how you found most of your bugs. In this case, we couldn't use this technique because we were looking for bugs in a very specific attack surface. But once we narrowed down the attack surface to a place which can be code which can be reached without any prior authentication, that's when we found this bug. But before we actually could confirm that it's a bug, we wanted to check that the buffer being copied into was actually too small to hold the data. If we look at the bug, you can see that there's a memcopy here, and we don't see any size check at all anywhere. And that means that we can specify an IE len as big as we want. And when we look at the function which allocates this buffer, we see that its size is only 44 bytes. While we have 1 byte in the length field, which means we can make a maximum length of 255. So 255 minus 44 gives us 211 bytes of overflow, which is actually very nice because it gives us a lot of leeway. Often overflows are small. They can be 8 bytes, 4 bytes, and then they're much harder to exploit. This actually gave us a lot more flexibility. And we started triggering this bug on various devices. So this is how it looked on my Samsung. This is an S7. Now this is pretty interesting. Look at what happens when I trigger the bug. So we see that the Wi-Fi system turns off. There is some indication to the user, but you should probably keep in mind that given that probe request is being sent out without the user's interaction, it's enough for the phone to be in your pocket and not touched, and still it will send out probe requests, and it will associate with an access point if it already recognizes it. And just the way you know, like you walk home and you take the phone out from your pocket and it's already connected. And that's because of this, this provision. That's because it looks for access points without any interaction from you. So in case you do trigger a crash when the phone is doing that, when it's automatically looking for access points, you will not see any user, you will not see any indication to the user at all. And after about 5 seconds, if you crash the chip, it comes back up. So other than a disruption of a few seconds for Wi-Fi connectivity, there's no indication. The story was different on my Mac, which was also vulnerable. It also had a Broadcom chip. Let's look at what happens. So I'm connecting to an access point which sends out the exploit. And boom, kernel panic. So this is a good time to mention that there's a difference in implementation between mobile devices and laptops. So in mobile devices, Wi-Fi chipsets are used in a setting known as full MAC, which means that they handle a lot of the work in association and processing. It's basically layer 3 stuff. It's known as MLME. And in laptops, in desktops and laptops, it's the kernel which handles it. So what we're seeing here is that the association process is being handled by the kernel, and it's choking on our bug and crashing. Now, this is not that good for exploitation, and we can talk about it later. In the meantime, we stay with mobile phones because that was our focus for this research. So now, let's continue. It's time for another quiz. Who remembers the second law of remotes? No assumptions. You cannot make any assumptions about the system. And again, the reason is that when you're attacking a remote target, you have very little indication of the state it's currently in. You don't know about its heap. You don't know about which files are open. You have a much smaller interface than you do, for instance, when you're attacking a browser and you have JavaScript, or you're attacking the kernel and you have syscalls. Remotes are completely different. You normally have very limited protocols, such as the association process, which is what we have in this case, and that's the only thing you have. You cannot make any assumptions. So many remote bugs met an untimely death because they couldn't meet this rule, because they had to make assumptions. Who can tell me one word, the main killer of remote bugs that requires you to make assumptions? Starts with an A? ASLR. Right. So with ASLR, you have to make assumptions about the system. And in this case, we don't have ASLR, so that's already one advantage. So let's see if this bug lets us meet the second law. So we don't want something very simple. We want to avoid a situation where our overflow puts us inside dynamic memory. That means we are in the heap and the locations are changing around us, and we have no clear indication of what we are overflowing into, because it could change from one execution to the other. What we do want is to be able to flow into a consistent address, an address we can predict. We want to be able to predict what's in that address. We want it to be as static, as consistent with memory as possible. We want it to just sit down and behave nicely, not move. It must not move. So, and the third thing we want is that data that we're overflowing into needs to be doing something interesting. It needs to have pointers which then are triggered in an interesting way. So let's see if this bug actually meets what we need. So the overflow is into a structure known as PS. It's a structure for handling power saving mode. Our structure is described as current WMMIE in the sources. That's the name. And both of them are static in terms of address space. They're allocated on startup, on boot. And given the deterministic allocations that the agent DRTE allocator makes, we can consistently predict the locations on a given system, on a given firmware. And it stays consistent across reboots. Even if you reboot the phone 100 times, the addresses remain the same. And once we confirmed that, that was a good lucky point. We wanted to check maybe, we wanted to check if our luck remains consistent. So we had a look at the PS struct. And we looked for interesting pointers, data which is handled in an interesting way, which helps us in an exploit. And what we found are all these timers. And timers are very good news when you're preparing an exploit, because timers are called regularly. They do something every once in a while, and they normally trigger other code, for instance, as callbacks. So, of course, that immediately seemed interesting. And we started digging around at what these timers do and when they're called. And we reached this function. As you can see, throughout this process, we were extremely lucky. First, in finding a bug in the association process, which doesn't require any authentication. Then in finding a bug which overflows into static memory. And now in this. So if you look at this code, towards the end, you can see a very clear write primitive. It takes an address from the overflowed object. It takes a specific offset from this address of 14 in hex, and it writes to that offset. So again, this is very simple, very clear, and we just, it was our lucky day. Now, we have a write primitive. Where do we write to? So, as we briefly mentioned, there's a table of functions in RAM, which is used as a way to patch functionality and add security fixes. What Broadcom do is, whenever there's a fix, whenever there's a patch, they change this function table to point to the patch. And the code in the ROM, at specific intervals, at specific points in the code, jumps to this table. And, there's basically hooks which redirect the code. The code can check whether there's any change. And then it comes back to the ROM. So this was a good place to overwrite because this table can stay relatively consistent across different firmware versions. And it's possible to predict what a particular offset which function will be in a particular offset. So we decided to write to that table. And then we had another problem in the exploit, which is that we only had 24 bytes for shellcode. So you can't do much with 24 bytes. That's not a place where you can put a payload which does anything useful. And that led us to consider where is a good place we can put our payload. Now, the way you normally solve these problems in exploit development is that you look for some kind of a spray primitive, a way to write to large areas of the heap with your code, so you can predict where this code is. We didn't really see this option in the Broadcom firmware. We didn't find any good allocation primitives in the limited protocols we had access to as part of the association process. So maybe, given that this is a Wi-Fi chipset, that this is a code which handles packet, can anybody make a guess about where we could write large quantities of data pretty freely? Can you make a guess? So there's a concept known as a ring buffer in network implementations, which is a circular buffer which holds packets as they come in. and then it overwrites the beginning of the buffer as the buffer gets filled up. And this is where packets are copied into after they're handled by the layer 1 chip. And this looked like a perfect place for us to put our payload. Now, the only thing we needed to do now is to write some egg hunting code, again, just like in the good days, which 24 bytes was just enough for that. It runs through the memory, looks for a particular header, and when it finds it, it jumps to it. And in this case, our header was in the ring buffer. Now, a nice thing about the ring buffer is that it's all RWX. So you can basically run code from anywhere you want, also in the ring buffer. So we jump to the ring buffer after finding our code. And this is the layout of the exploit buffer that we've eventually ended up with. You can see we were able to use the overflow to put our fake timer object at the beginning. It jumps to a shellcode stub. Then it jumps to the egg hunting code. And eventually it jumps to the ring buffer. Now, do you remember the third law of remotes? You must leave the system in a consistent state. So we had to clean up a bit. We had to restore the buffer that we've overflowed. And we had to restore the pointers and make sure that we left the system in a consistent state just the way we found it. And with Broadpwn right now, there's no indication or any crash after you run the code. So you just run your payload, you install your hooks, and the system stays stable and consistent. Yeah. And this brought us to the really interesting phase. So when I was starting work in this field, we had worms. We had this self-propagating malware, which could basically run wild over the network. Can anybody remember any particular worms which were famous? Just toss out some names. Yeah? Yeah. And Stuxnet too? Yep. So there were quite a few in the good days. And they died out together with remote exploits. Remote exploits became no longer possible, so worms pretty much needed them to propagate. But Broadpwn is a perfect bug for that kind of thing. So we thought this is a pretty good occasion to make the first Wi-Fi worm and the first network worm in a few years. So the way this is implemented is after you run your payload in the chip, you put some hooks. Yeah, you put some hooks in the functions which handle packets, and you basically re-implement the code which triggers a bug, but from within the chip. So luckily the bug is pretty simple to implement, so the limitations are not that big a deal. And we were able to implement some basic infecting code from within the firmware, and still kind of were able to work within the space requirements, like the space limitations. And that's it. The way this works now is a phone gets infected. It starts looking for probe requests. It sends out, whenever it sees a name and SSID, it sends out a response, starts the initiation process, and starts infection. Now, the way it works now is we don't do much other than send out a probe request from an infected system saying, I am owned. That's the only indication we give out. So what we're going to do is we're going to show a demo of initial infection, and then we're going to show how it skips from phone to phone. And, oops, yeah, and then we'll actually see the packets being sent over the air. So now I'll switch laptops. HDMI. Yeah. Okay, I hope there's nothing embarrassing on my laptop. Yeah, is this good enough? Okay. So I'm going to turn on Broadpwn. Wait, let's see, everything is connected. Yeah, my phones. Let's start with this one. So I've not given any offering to the demo gods. And this demo is kind of complicated because, well, it requires us to spray a large number of packets into the ring buffer. And given that there's all these guys here with their mobile phones, it might be a bit tough. We might need to do a few retries, but we'll give it a shot. So first of all, we're going to run Broadpwn. There's going to be an access point now. It's going to be, the name is Broadpwn test. You're welcome to connect and try to crash your phones. Yeah. Okay. Fine. What we're going to do now is we're going to run a spray of beacons. You're going to see an access point, AP0 to 4, using something. We're using a tool called fake AP. The only thing it does is send out our payload in a spray over the air, so it fills up the ring buffer of the first phone. Right, so we're going to run it. Now, okay, it's running. Now, by now, actually, my phone might be infected because it's supposed to send out a probe request. Let's look at the log. I hope it's not infected yet. Yeah. Wait. Oh. We need to parse the logs because we're using a special tool called DHDutil, which extracts them from the chip. They're not on the kernel, they're on the chip. Okay. Has it been infected yet? Not yet. Okay. I'll just like give it a rub to start scanning. Okay, yeah, sorry, it was in, so you can see that it's okay, yeah. Can you see payload triggered? So what it does here is it starts so the payload needs to restore the CPSR because, you know, an ARM CPSR holds the state for interrupts and everything, and the code which basically there's a reason we need to restore it, otherwise the chip crashes. Then we restore the struct, the power saving struct. It's called WLCPM-ST. And then what we're doing is we're just sending probes which say I am owned and waiting for probe requests. So now let's look at the other phone, which might also already be infected. So probe requests get sent out about once a minute. Now, the infection is a tricky part. It might not work. It didn't consistently work, but I'm hoping I'm going to get lucky. Because you notice that on this project, we got pretty lucky a lot of the time, right? So let's hope this luck stays all the way through. I'm going to check the log. It might be already infected. I don't think it's infected. Now you can see the hooks, but yeah, okay. So as you can see, the infection process is pretty fast. It's just an exchange of 4 packets. And it's already sending probes. Yeah, and here the same thing, Broadpwn, payload triggered, and all that stuff. Now what we're going to do is to have a look to see if we can see these, just to prove that these phones have been owned. We're going to sniff using AeroDump to see the IM-owned packets, to see if they're on the air. Now I'll first try to work with AeroDump just like that. Although there's no chance we're going to see anything because there's all of you guys here and it's just going to get swamped. So we're going to run some code to filter particular MAC addresses, which I know are the MAC addresses of these phones. But first, just for entertainment, let's have a look at what's going on here. Oh, so these are it's pretty interesting just to see like who's here. These are access points, but if we move to like a different channel, you'll see that MGM Resorts, which is like the open Wi-Fi that the hotel has put in here, is on channel 11. So if we switch to some channel 2 and put like encryption open, it's a way to trick AeroDump into showing us just clients. So let's just look at clients which are here and unassociated. Just to repeat like that entertainment we had before. Let's look at like the names being sent out here. Let's look here. So here is Eliza. Is anybody named Eliza here? Somebody's been to Brussels. Did you see it? Wi-Fi Brussels. Here's Eliza again. This is pretty interesting, right? Okay. Somebody from China. Cool. So now I'm just going to run TCP dump from this script, looking specifically for probe requests coming out from these 2 MAC addresses. So I'm just running it, letting it capture. Now, the hooks I put are in the function which handles receiving packets. So whenever it receives a packet, it sends out a probe request. So that's why I need to like play with the phone a bit, let it scan so it receives lots of packets to make sure that that we catch the probe requests on the right channel. So I'm playing with it a bit. Yeah, I think that should do the trick. Okay, and show probe. Okay, yeah. So you see we have 2 stations sending out requests, IM-owned, and that's it, basically, game over.